Hello everyone. Welcome to our final CATIA Systems Masterclass of the year. Our topic today is software-defined products from system specification to integrated software. During the session, you will explore how Dassault Systems is transforming product development with its software-defined product approach. Whether you are working in MBSE, electrical, electronic engineering, software, or testing, or simply eager to expand your knowledge, you are at the right place. All these topics will be covered and presented by my guests, David Guyon, Clément Bayerguet, and Louise Offer. During and after the session, you will be able to ask questions in the Q&A section, and speakers will take some time to answer them. Let's dive into the future of integrated model-based software development. David, the stage is yours.
Thanks, Gitana. Hello, everyone. So the topic today, as said, is software-defined products. In other words, how can we go from system specification to integrated software? Today, the team here to present is composed of Clément, Louis, and myself. The three of us are members of the worldwide CATIA Systems, Electrical and Electronics and Software Engineering team, which is a CATIA pre-sales organization. So, just to give a few words about the software-defined products architecture, market, and challenges, what you can see in this picture is, as you know, the number of features that are available in vehicles, planes, and many other systems are growing. So it has an impact on the software because the software is more and more present in our systems. And also, the second big fact is that the time to market, which was on this graphic, for example, a few years ago, is now very reduced. And now a vehicle can be out 2 years after the beginning of the engineering. So the challenges are to first handle the electrical, electronics, and software architecture complexity, to design optimized architecture, and to reduce and secure the time to market. So for that, what we propose is to have a fully integrated approach from system-level architecture development down to the disciplines, but in between, to ensure consistency, the job of the EE&S architect is very important. So that's on which we will insist today first, and then on one of the disciplines, as you will see. So the typical approach is first to start from the customer needs to specify services, features, and so on. So a classical approach at the system level, from which you will get some specification requirements, use cases, architecture, and so on. Once the architecture is modeled, then you can go down to the disciplines, but articulate them on a main element, which is the electrical and electronic software architecture. This architecture has to be consistent with the feature growing complexity. The steps are first to design the hardware topology and the software architecture, to allocate the software components into hardware equipment, to define the communication between the elements, and then to come back and optimize this architecture thanks to an optimized system mapping. Once this architecture is defined, next step is to go to the disciplines for the detailed design of physical equipments. That's the point where we are with the disciplines. That can be, for example, electrical, software, electronic PCBs, and so on. What we will focus on today in these disciplines is going down to software from system level. That's the title of our webinar today. For that, we will illustrate what we can do as a system design workflow thanks to Dassault Systèmes CATIA solutions. So first, for the system architecture level, of course, we have the solutions integrated into CATIA Magic or no Magic portfolios. That's what I will quickly present to you on the basis of an example. After that, Louis will introduce you a new solution which is CATIA Systems, Electronics and Electrical and Software Architect. It's an integrated MBSE solution for EE and software architecture design. The goal is to ensure a digital continuity from system design down to implementation and to enhance the cross-disciplinary collaboration. To finish, Clément will introduce also a new solution, which is CATIA Systems Software Production Engineer. It's a model-driven software development environment based on CATIA Magic also, under the form of a plugin that enables you to generate code from models or to do the reverse engineering of existing code into models. For that, I will introduce first an example which is based on aircraft, the seats of the aircraft, and I will start this by the system. Let's go quickly on CATIA Magic. Of course, I will now go into all the details, but let's consider that here we are addressing in the aircraft the cabin, and in particular in the cabin, the seat row. The objective in this demonstration is to show you how we can have an integrated workflow, integrated models, consistent models from systems down to EE&S architecture and down to the disciplines, in particular software definition here. So let me go into a 3D experience platform to show you we have in fact the various models in the platform also that we can just display. If I go into the system level model, I will not go into all the details, but let's consider that we have stakeholder needs. From the analysis of the stakeholder needs, we have illustrated some use cases. The main one here is to provide passenger seat comfort. Of course, it will include the use case to provide position adjustment capacities and to ensure the passenger safety during takeoff and landing. To do that, I go through the model. We have, for example, elements about the architecture. So the passenger seat control, the cabin crew interface, the passenger display, and so on. If we come back to the use cases, of course, the functions that are needed to ensure the passenger seat control are allocated to components. That's what we see here on this activity diagram. We've allocated actions to elements. So I will not go deeper into detail at this level. I will leave now the floor to Luis that will explain you how from this kind of architecture, we will now go deep dive into the electronics and electrical and software architecting. Luis, stage is yours.
Thanks a lot, David. So as David has explained to you, the EE architecture, it's really the linchpin or the bridge that is connecting the high-level system specifications. So this is typically what you would do with XML, like David showed to you, and what we call the detailed physical design or detailed implementation, which could be software or electrical or PCB design, for example. So you see, it sits nicely in between and connects the dots between all the different disciplines. So it is composed of three main parts, which is first the software architecture. So this software architecture, of course, is the refinement of the functional architecture coming from MBSE or early MBSE, right? We also have the electronics architecture, which is also called the hardware topology. So, of course, this is also linked with the logical architecture that you define in MBSE as well. And then the last part is the communication matrices. So here we start to define all the messages, and we're going to see that later. So these are the three pillars of the EE architecture. And the idea for the software architecture is to first define the high-level software architecture for the system, identifying all the different interfaces so that we can then send this information to the software team that will then focus on defining the detailed implementation of the software, respecting the interfaces. It will be the same case for the hardware topology as well. Here we start to define the different hardware architecture, we will see later. And the final thing that we have to do here is the what we call system mapping, where we are allocating the software architecture to the computing resource in the hardware, and also the communication matrices to the communication bus. So going back to the pillars of the EE architecture, like I said earlier, it's composed of three main parts. The first part is the hardware architecture. So within that, we define what we call the hardware topology. So it is a system. So for example, the cabin topology, right? And within the cabin topology, you're going to have different types of components. For example, the ECUs, the electronic control units, you're going to have actuators, sensors, etc. And then you go into the software architecture, which is the second pillar of EE. Here you start to define the high-level software compositions, so a group of software, as well as the atomic components, so units components, software components, as well as the variables, of course. Then the last part is the communication matrix. And the idea of the communication matrix here is to start to define the messages, the priority of the messages, the timing, etc. And you put all of that within the frames. After doing all these activities, then we go to what we call the system mapping and optimization. Here we are allocating the different software components to their corresponding hardware components. So these hardware components will be responsible for executing the software codes. We also allocate the data elements, which is the software interfaces, to the corresponding system signals, so in order to be able to route these signals within the hardware topology. And finally, we also allocate the communication matrices to the communication bus that we have defined in the hardware topology. And like we have guessed already, all these activities will be done in CATIA Magic. So it's a special plugin. I don't like the word plugin. I prefer the word solution because it's not just an add-on. It's a global solution that we use within CATIA Magic to execute this part of the process. So it's composed of, like we said, modeling domains such as XML or UML. It means that you can create your software architecture either in UML or in XML. So the tool gives you the opportunities to do both. We also have dedicated diagrams as well to create the software or hardware breakdown structure. So this is the block definition diagrams, or the internal interactions, which is the internal block diagrams. So we have dedicated diagrams for that as well. And you will see that we also have the possibilities to import different types of files. So CAN-DBC files, for example, for the communication matrices. Okay, so enough of presentations. Let's go into the tool to see how the tool actually works. I will just switch my screen quickly. Yes. So when you successfully install the solution, you will be able to create a project, right? So you would have dedicated templates in order to create your project. So depending on which domain that we serve, you can either have the EE architecture for the transport and mobility industry, or we can have it for aerospace and defense. So of course, depending on the domain you have more technologies, for example. In this example, we are going to start with the hardware architecture, right? Within the hardware architecture, you have dedicated packages. So in this example, we have, so all this is predefined, right? So once you create the project, you have all these dedicated packages. Within the packages, you have what we call the connector type. These are basically the communication technologies that the components would use to interact with each other. So within this, you have things like the CAN interface, you have Ethernet, you have Wi-Fi, you have ARINC 429 for aerospace and defense, you have many other interfaces. And within the hardware component package, then you have dedicated packages as well for things like actuators, communication buses, etc. And you have dedicated packages also for the topology. So this is where you start to define the system. So for example, cabin management. And then the last package here is the VLAN. So here you start to define the VLANs for your Ethernet communications. And the good thing with this plugin is that you have dedicated menu to help you create objects, right? So you can create either EE architecture elements or the diagram. So this is something that comes with the solution. And when you are in a specific package, the tool also constrains you or helps the users to not make mistake by enforcing them to create specific objects. So because I'm in, for example, the actuator package, I can only create actuators. It will be the same case for communication buses, etc., etc. Okay, so let's look at the seat row topology, for example. Here we have defined different actuators with their different instances. We have defined the passenger control units represented as an ECU, etc. And we also see here that we have, for example, the CAN bus. So this is mainly for the communication, CAN communication. If you go into the internal block diagram to see the interaction between the different components, here you automatically see, or you basically see how the components are connected to each other. So for example, you have the seat electronic box that is connected to the seatback LCD via an Ethernet switch. And you also have, thanks to this legend, you are able to quickly see the different types of elements that we have here. And you can, of course, filter based on that. So if I, for example, filter based on the CAN communication, I only see the components that are linked to the CAN communication. You can save this, for example, and then use it for review purposes or validation purposes. That's it for this part. If we go, for example, to, let's just go here. Yes. So I spoke a little bit earlier about the VLANs. So with the VLANs, you are able to create your virtual local area network within your topology. And thanks to the legend as well, you can automatically filter based on these VLANs. So in this case, I can say that it has filtered based on this specific VLAN called cabin, right? So what is good about this filtering is that you can automatically see, for example, that there is a missing communication or connection between the ECU and the hub. So in other words, we need to, thanks to this legend as well, I can then select or add this specific connection, this specific Ethernet connection to the VLANs. And now when I filter one more time, I see that it's now fully connected. So it's a way to kind of also validate the model. Okay. There are also some other validation that the tool helps you to do. For example, if I want to create a CAN communication, or let's say an Ethernet communication between the seatback and, for example, the CAN bus, it will not let me do that, or it's going to throw an error, basically saying that you cannot connect the Ethernet to a CAN bus. Right? So you see it throws an error here. So I'll need to delete that. I will delete that. But however, I can create to this one, and you see it automatically creates the corresponding Ethernet ports and the connections. So these are little ways the tools help the users to model correctly the architecture that they would like to define. So I'm going to delete that. And that's it for the hardware topology. Let's go over to the software. So with the software architecture, it's more or less the same as the hardware architecture. You have a dedicated template to help you to create a different software artifact. In this example, we have the different artifacts, such as, let me start with that first. So here you have the software architecture components. You have different types of components that you can create. Then you also have the software interfaces. So there are both two of them. The first one is the signal-based interfaces. So with this, you start to define, for example, the sender and receiver interface, as well as the client-server interface. So sender-receiver is mainly for interfaces that are asynchronous. So meaning that you send an information from one component and the other component or the receiving component just receive the information. It doesn't need to, for example, send any information back to the component that sent it. And we have the client server. So this is more or less client and server. So it's synchronized, synchronous communication. So where one component is sending the information and it's also waiting for an answer from the corresponding component. So we have the signal base and we also have the service base. So this is more based on, this is what we are seeing now in the industry, based on the software-defined vehicles, where we are defining services. So a specific component is sending a service and other components can subscribe to this service. And this is typically what you have. Of course, you have the legend as well to automatically see the kind of interfaces that you define. And then again, for example, this specific C controller will then be utilized later to generate the software implementation for this specific component. And in this example, we have the seat management that has different components like we see, and then we can also see the internal block diagrams and how everything is connected. So let's go to the communication matrix. So within the communication matrix, you have dedicated menu as well. And you also have this table, which I would expand now. What's good with this table is that you see all the types of communication matrix that you can create. So for example, CAN, Ethernet, FlexRay, ARINC as well, etc., etc. So if we take the CAN seat, for example, you see that we can also create the different types of frames. So the standard CAN frame, the standard, the CAN extended frame, the J1939 for trucks, etc., etc. So depending on what you'd like to create, you have the possibilities to create as much as you can. Yes, so you can do the same for Ethernet as well, etc. And of course, when you go into the CAN frames, you then see your messages as well. And within that, you can, of course, visualize it on the table. You see the more information about the messages. For example, the bit start, the size of the message, is it the multiplexer, is the resolution, etc., etc. So this is a table that comes by default. And of course, if you need more information, you can also add to this table. So for example, if you need the documentation, you can get that. If you want to see the consumers of a specific signal, you can also have that within the table. And you see that it's added just at the right here. So you can add basically and also reduce the attributes that you would like to see on the table. And what is nice as well with this is that you can also import the standard CAN DBC files. So the tool lets you to import all the necessary information that you need. And in the next release, which is by 26X, CATIA Magic 26X, you also be able to import and export the ARXML files as well. So let's go to this interesting feature as well, which is the matrix editor. So initially we see the table, but we can also see it in the graphical representation, which is what we have here, for example. So here you see all the messages. You also see the information about the message. For example, the name of the message, the size, and etc. And of course, this table it's not static, it's live. So what that means is that if I change or I can manipulate this table, and of course the value is going to change within the second table here. So it's live. So it's basically telling you that you can either use the communication matrix table like you have here, or you use the graphical representation. So for example, if I try to find the lumbar request, which is number two, this one, yes. And here we see, for example, the bit start is 24. If I move it, sorry, not that one, number two. It's this one, yes, it's this one. And you see that I can also increase the bit size from the table. You see it has changed to 4. All right, so it's really interactive. The users can either manipulate the tables from the tabular view, or they can use the graphical view. So I can also reduce the size, and once I do that, it reduces there automatically, and I can put it in the location, and then you see that the bit size has changed. And it's two ways. So what that means is that if I change this value to 3, you see the 2 automatically identify that there's an error, meaning that the signals are overlapping, right? You see the error both on the graphical view as well as on the table. So I can change that to 2. And the error disappears. So this is a way to basically validate your model while modeling, essentially. Okay, so that's it for the communication matrix. Let's go to the final part, which is the system mapping. All right. So the system mapping is basically how we can link all the projects together. So what this means is that as the EE architect, you can be designing the hardware topology, right? The software team or this EE architect, depending on the organization, can define the software architecture as well as a communication matrix. And what we have with system mapping is the way to group all the projects together to optimize all the models and also, basically optimize the model. So the first thing with system mapping is to do the software architecture allocation to hardware. So on this table, you have the software architecture and you have the hardware, and then we do the allocation between the software and the hardware. The next thing that we do is the data allocation. So you have the interface and the information of the software, right? We need to allocate that to what we call the system signal in order to be able to route these signals within the hardware, respecting the interfaces as well. Then the third thing that we have to do is the basically the communication bus allocation. So remember that within the hardware topology, we had, for example, a CAN communication matrix, right? Then we allocate not the CAN, not communication matrix, but the CAN bus. Here we allocate the CAN bus to the communication matrix that we define. And finally, we have the signal routing. So basically, we are going to route the signals within the hardware. So I'm going to show you what that looks like. So within the signal routing, we select the signal that we would like to route. We see the producer and the consumer. Then we select, for example, which producer and which consumer. Then we see the possible paths. So in this case, there is just one path, but there are cases where you have different paths. For example, you have safety reasons or redundancy reasons. You have different paths. So within the signal routing, then you can specify exactly which path you would like your signal to go from. Of course, you can also see the ports as well. And like that, you are sure that the signal is being routed using the right port. So when I select that, I'm able to route the signals. So thanks to these activities, then we would have the global view. And in this global view, we have at the top, the software architecture. At the bottom, we have the hardware topology. And then we see the allocation. We see the allocation between the software component and the corresponding hardware. Not just that, we also see the information that is flowing from component to component. So for example, we know that these signals is going to the CAN port, and these signals are going away from the CAN port, for example, to the SIT electronic box. So that's a way to actually validate your system, that the software, right, is allocated to the right hardware component using the right interfaces, right? And then you also have the possibilities to see this with a simulation view, right? What I mean by that is that if I select, for example, the signal that I want, you would see on the hardware the from, for example, and the to. So in this case, the information is going from the SIT electronic control box to the comfort linear actuator. So of course, you can select all the signals, and then you see all the way the signal is flowing from one component to the other. And that's pretty much it. I will just go back to the slides. Sorry. So what have we seen so far? We've seen an end-to-end digital continuity. So starting from the systems architecture down to EE and down to the, we haven't seen the implementation, but we'll see that with Clément. So like that, you have a full end-to-end traceability starting from systems architecture to the detailed discipline implementation. We have seen an architecture-driven workflow. So all the architecture that we defined from the MBSE part, we utilize them within the EE to within EE architecture as well. And this information will then be utilized within the software implementation and other disciplines, for example, electrical. And we've also seen an assisted and automated data generation. So you see the live validation of the communication matrices, the live validation of the modeling when it comes to the hardware architecture, and much more. So that's it from my side, and I'll let the floor now to Clément to show you the detailed discipline implementation of the software.
Thank you, Luis. So now for our final step on our workflow, I'm going to talk about the physical design and more specifically the software part. Where we are going to use a new feature available in CATIA Magic called CATIA Systems Software Production Engineers. This new feature has various use cases. The main one and obvious one is to generate code from the CATIA Magic model. So it can either be CSML or UML to C, C++, Java. Then once we have generated this code, we also give you a framework to validate the generated code. So you can write quick tests to make sure that the generated code is behaving like you intend. And as this can be done in a code editing software, we also can easily integrate AI features in here. The other use case, the reverse code engineering use case, is to do the opposite, to take the code and to generate some models. So this can be done for two ways. Either you already have written some code and you want to create a model for it for traceability, storage, certification purposes. Or you have a model, you generated code from it, and now that you've made some modifications, some edits in the code, you want to store those edits back in the model to make sure that the model is your single source of truth. So how do we do this? The tool has four layers. We first generate the component layer, which is the algorithmic part of the generated code. This is C or C++ mainly, and is not specific to any hardware. From this generated code, you can add a target abstraction layer in order to compile this code to a specific target, which would have also a specific hardware abstraction layer. In our target abstraction layer, we need to have all of the things regarding the scheduling, the messaging, the timing of the different events and messages that are happening in our system. And we are giving you some target abstraction layer in order to directly implement your generated code for some specific hardwares, but it's something that is quite open. And if you want to create your own target abstraction layer, it's easily possible. So let's look in the tool, how does it look like? So in CATIA Magic, the first thing that you need is, sorry, wrong button, plugin, is the plugin called CATIA Software Producer Client. This will allow you to, in your containment tree, to create code generation configuration diagrams, which is the object that I've already created and opened here. In those diagrams, you can create different configuration. And here I've already created a C code generation, CPP code generation, sorry, C++, once you do this, you specify the name of this generation and from which element you want to generate it come from. In here, I've already done it for the seat controller, which is an object in here. And this seat controller is composed of lots of different objects with attributes and operations. Below, we have state machines that control the expected behavior of our system. Now, the only thing that we need to do is to select which code generation we want to use. Here it's called code architecture, the first one, and generate some code. This step is done locally, so it's quite fast. And I have all of the files created in here. So let me close. In the files windows, under the code architecture, which is the code generation I've just used, I can see all of the files that have been generated. And I can double click on any files to see the content of it. What's really interesting is that in every files, in lots of places, we have actually the information from where this code has been generated. And if I click on it, I have the link with the model. So it's quite easy if I want to update things, or if my code is not behaving the way I thought, I know where in the model I can make the modification. If I want to make them in the model, or I do them in the code and then I use the reverse code capabilities. This is just a viewer, it's not an editor, but it's totally possible to open this code in any IDE that you want. A nice feature that we can also use once this C++ code is generated is that we can actually load this into a Node.js server. And if we build around it a couple of buttons and images, we can actually interact with the model. So for example, here I clicked on the leg rest and I can actuate. I think my server is down. Yeah. I think, yeah, sorry, my Node.js server is down, so I will not relaunch it now, but if it was up, you could directly interact with the inputs of the model, which are the button regarding the leg rest and the backrest position, and directly see either the values on the bottom left change, as well as the picture as it's what has been defined with this interface. So a possibility for some systems that you want to interact quickly. Something else, going back to CATIA Magic, that we can do is if we want to take this code and check the behavior in another way, we can create a component tester. So just by clicking on it, I can create the component tester. Same as before, I need to give it a name. This time, I'm not going to specify an element from the model from which I want to test, but which generation I want to use. And just for this demonstration, I'm going to tick the box generate test case example. Now that this is done, I can launch this new generation. And so basically, it still takes the same C++ code, but embeds it inside a test harness, let's say, that I can open from any IDE, for example, VS Code. So in here, as I've asked to generate some test cases example, I have a C test case, which is just logging a message and running the model during 10 seconds. Same thing here in C++. And if I want, I can list the test case. So first it's making the files, but then it will run the list test case. Here it's quite obvious, but let's see. Now let's make, you should see. So I have the 2 test cases available. And what I can do, going back to a test case, I can either edit this one or create a new one. So I've already prepared something that we call my C test, in which I'm setting input values and writing those values, then running the system and checking the output values. So now, instead of running the list test case, I'm going to run the test cases themselves. And so I'm going to have an information about the behavior of my system. So here I have in the terminal a quick recap that I can also find in my logs. And if I want to specifically look at the test I've written, we can see that I've logged the messages at the beginning, then I checked some values. The value seen was 3, expected by what I wrote was 3, so it was fine. Same thing for the second line, but as you can see, the last line is in error because the expected values is not the one that is being matched. So this is to quickly check the generated code. It can be quite useful, and you can extend here the test cases possibilities as much as you want. The last feature that you can use also is the FMU code generation. So it's already prepared it's another code generation configuration, but I can directly select it here. Click on the generation button. And this one, as we need a compiler in order to create an FMU, it's using a capability that is stored on the server on which I'm connected. So it's a bit longer as it needs to upload and download some information. So it first create the code and then compile it. I've already created the FMU before, so I can go to the next step. In another tool called CATIA Stimulus, I've already prepared the test environment of this FMU. So maybe you recognize this diagram as Luis presented it in a previously. And we can import the diagram from CATIA Magic to Stimulus using a plugin that lets you get the blocks, the inputs, outputs, their names, their types, so you don't have to create the diagram from scratch. And I've created a simplified version because in here we have 4 seats in a row. We have only 1 seat electronic box for each row of seats. But I can focus only 1 seat, which is composed of 1 comfort linear actuator, 1 lumbar relief system, and 1 comfort rotary actuator. So if I look into this simplified version, it looks like this. The FMU that I've generated, I've already imported it previously, and you can see I've retrieved the names and the directions and the types of the signals. And so I can simply drag and drop this FMU into my block diagram. So now when I simulate, I will have an on the output of this box, so the footrest position and the backrest positions, the output produced by the FMU, which is coming from the generated code, coming from CATIA Magic model. And we are going to check the behavior of this box according to some safety criteria that are written in an observer. So I can launch the simulation. And if I bring back some interfaces panel that I've prepared that let me directly interact with the simulation, I can launch the simulation and make sure that when I'm in, for example, taxiing state, I'm not able to deploy my my backrest. You can see in the diagram the different requests I'm making, but on the second graph, as well as on the gauges here, nothing is happening. I can ask the seat to go up, but never down. But if I'm in flying mode, now I can request the seat to go down and to go up. Another use case that maybe we have not thought about is that if I ask the seat to go down, and then I'm changing state, for example, to taxiing, now my simulation turns red, and I actually have some information about what has been detected. So I have a violation of an observer, and the observer that is being violated is the observer that is requesting that we can only deploy the backrest if we are in flying mode, which was not the case, but we didn't thought about the case if we send a request in flying and then change state. So maybe it's something that we want to protect in the future, and so we can do this iterative process of editing the model to generate an updated version of the code. And so we detect errors even before testing in the physical world. To conclude, going back to my slide deck, we have a lot of benefits with this tool. Obviously, the biggest one is the reduction of the cycle time, and thus the development cost and the time to market. So it's a big advantages knowing that what David presented at the beginning of this presentation. We keep all of the knowledge in the model. That way, when we reuse for future version the model, we start already from the good model, which is not always the case when we validate things in the code. And the FMU that I showed you, for example, we can, so I showed you how to use it for validation purposes, but you can also embed it in other FMU compliant tool in order to wider test and connect different systems. Obviously, it helps you develop it helps you develop the code, and it helps you validate it. And so the last step, the last benefit is the continuity and the traceability between all of the different parts of the process that we showed you today. And I'm giving the hand to David so that he will showcase this feature.
Exactly. Thanks, Clément. So yes, we wanted to end this webinar on one important fact. I started by saying in the beginning that we need a fully integrated workflow from the system level down to the disciplines. So we focused on software, EE&S and software. And what I would like to show you here is that we have the benefits shown by Louis, shown by Clément, but the one very important is this digital continuity. So here what we see is the 3D experience platform with all the models that have been made at the system level for the EE&S architecture, for the software production. All these models are here in the platform. They are managed thanks to CATIA Magic Power BI. And I have made a traceability scope, what you have here on the screen, in which it is a simplified view, but on which I have taken some elements from the model and I have put them here. So what I would like to check with this view is, does each element in my model got a coverage? So let's do that. So we put element, we put some channels between the elements. So from system, EE&S and software levels. And if I switch from this edition view to the traceability view, I see that, for example, 40% of the stakeholder needs are covered by a function in the use case or and an element in the passenger sync controller. These ones are also, from the system level, covered by EE&S architecture elements. And some elements of the software architecture are covered by the seat controller architecture from which Clément has produced the code. So clearly, you can see here, you have a kind of dashboard that shows you what is covered, what is still to be covered in your project. If we go now deeper into this view, so I double click here to see the traceability or the coverage of these elements. I can see that my stakeholder needs are grouped in two families. If I take this one, for example, it is covered by this and these actions, and allocate it to this element. Okay, we can do that for every element, but we can also have an impact view with all the elements that belong to my traceability scope. So I clicked in the impact view here. You have in green the system level, in blue the EE&S architecture, in red the software definition. And you can see, for example, that this need is covered, of course, by various elements, but each one has an impact on another element. So I can see also the upstream and downstream traceability. For example, if I select the seed controller, I see if there is a change on this element, what can be impacted as an upward traceability. So that was the technical element we wanted to show you. Before going to the Q&A section, we would like to invite you, if it is not already the case, to follow the CATIA MBSE user community. You have here the flash code to access to this community. On the community, we are sharing tutorials. You can learn customer best practices. It's a community of exchange, of course. So we will share also the replay of past digital events like this webinar. And you will be able to exchange and connect with users, but also with CATIA MBSE systems experts. So thanks a lot for your attention. And we have now a few minutes for Q&A.
Thank you so much for your presentation. And yes, we have a few questions and we still have a few minutes left to answer them. So one question is, what about the other physics disciplines? Do these new tools include thermal, mechanical, magnetic, etc. physics or not?
Yeah, I see this question by Gulkan. Thanks a lot. You asked the question at the beginning of the presentation. So what you see here is that we focus on the software-defined products. So we articulate all the EE&S architecture. It's clearly a discipline-oriented tool. Okay, this is not yet, let's say, expanded to mechanics, thermal, and so on. If you want to do that, you can have a high-level view in CATIA Magic. Why not? But I think if you want to model the physical equations, do simulations, and so on, we have maybe other tools. Not maybe, we have other tools to do that. In the Daimler portfolio, for example, or in the Simulia portfolio.
Okay, thank you so much. And also, I have a few questions on our community, which you just mentioned. EE&S plugin, are the existing element types fixed or can we extend them?
Your mic is mute,
Luis,
Luis.
Please unmute, Luis.
Yes, thank you. Thanks. Yeah, that's a good question. So for now, we have dedicated, let's say, customizable attributes that the tool provides to you. However, of course, you can extend this profile, right? So if, for example, there are certain communication technologies or specific components or interfaces that you'd like to have, you can extend the profile, of course. But the idea is to have a global profile for the different industries, aerospace, transport and mobility, and other industries. And if you need to extend this profile, of course, you can extend it. It's a capability within CATIA Magic.
Okay, and how are CATIA Magic models linked? Are they used in projects?
So, do you want to answer or do you want me to answer, Luis?
Go ahead, Go ahead, yeah, go ahead.
Yeah. Okay, so if we can come back to my screen. In fact, what I have shown here is that we have various models, okay? So we have the possibility in the 3D Experience platform now to see the relations between the models. What we have done is one model for the, let's say, SysML MBSE system level, okay? Other models that are here for the EE&S architecture, and one for the software definition. What we can see here, for example, okay, let me just take this one, for example. Oh, the one I want to show you is not in my recent. Okay, but no problem. Let's select, for example, the. Yeah. So let's open it. So here I took a project in which I have reference all. Oh, excuse me. Reference all the projects. So I can see which are the use models. So in here, it's the one that gets all the other elements. I can see the software definition model, can see the system mapping. The three other as profile here. But as Luis shown you, the system mapping is using use models and so on. Okay, this one is also connected to the software to MBSE and so on. Here we are at the project level. What we have done also is more than that in these traceability channels. We made in between, let's say, system, electrical, and software elements, we made some traceability links directly in CATIA Magic to show that we are refining. Trace here is a choice. We can choose refine links or whatever you want, in fact, as types of links.
Okay, so thanks a lot. We have a few more questions, but we don't have time, and I will write these questions in our community under this post, and my colleagues will answer these questions. So thanks everyone for being together with us, and I will wait for you for our next sessions next year. And now thanks for my team, and see you next year.